Hello and welcome to the fifth lecture on Geological Activity Explained. And today I'm going to discuss why most tectonic fractures are small and only a few ones are very large. When we see a fracture system or pattern, such as here in the Bristol Channel, more specifically at so-called Nash Point, I'll explain in a moment, in southwestern Britain, there are always many more comparatively small fractures than there are large fractures. Now, why is this the case? What are the reasons for these fracture size distributions? And eventually, how do these fracture size distributions explain earthquake size distributions? I shall be looking mainly at fracture patterns in sedimentary rocks. So this is different from before, where I mostly look at volcanic rocks, primarily in limestone and shale and mudstone. And my field examples are from parts of the north coast and the south coast of the Bristol Channel in southwestern Britain. So the areas are here, close to this place called Nash Point on the north coast. So it's in this area here mainly. And on the south coast, I'll be looking mainly at outcrops between the villages of Watchet and the village of Kilve. So these are the two main areas where we take the field examples, but the conclusions are universal. They apply to any fracture patterns really in the world. So here is Nash Point again, but now we are looking at from a different viewpoint, showing fracture pattern in layers of limestone primarily. Now the fractures here, and those I show you in the talk, are mainly of two types, namely joints. As I show here, all these smaller fractures are joints. And then faults. The larger fractures seen here are faults, but there are also small faults as well. But generally speaking, in a fracture system, the largest fractures tend to be faults. Now, the orientation of the joints varies, and it does so for two main reasons. First, the joints are in different layers. For example, if you look here at A, we see joints in A here and spreading out here in this limestone layer, but there's another layer here, as you see clearly, and in fact we see the edge of another one there. So the joints are in slightly different layers, and that means that the layers may have had different local stress fields when the joints formed, as I discuss later. And in addition, we will see and discuss that many of the joints change their orientation when they come close to faults. And I'm going to explain that as well. But let's first look at what the joints look like and the faults look like on the ground. We look at the places A and the place here B. So here we are at location A, and you see here the lighthouse of Nash Point and the cliffs behind here. The lady here is standing close to the center of this curved pattern of joints, and she's standing in a fault. She's standing in a fault. They see here different layers of limestone behind her. And they commonly curve around parts of the faults where there are some notches and jogs, some irregularities that were kind of hindering the fault displacement for a while and concentrated stresses. These jogs and notches, they concentrate stresses and may lead to abrupt change in the orientation of the joints around them, and sometimes in beautifully curved joints, as we see here. Now here is another place along a fault, this one here, where the lake is standing. And now we see the joints kind of curving away from this notch here. And that's because here was a stress concentration along the fault. This is the fault here. And that led to changes in the local stress field at the time when these joints were forming. Again, you see here, these joints are in this layer, this limestone layer, but there's another limestone layer here and another there, and it continues up the cliffs. The beauty of this all is that the joints, they map out the principal stresses at the time of their formation. They follow the stress trajectories as I show in a moment. So here is an example from a two-dimensional stress fields. One is around a circular hole here on the left-hand side, and the other one is around an elliptical hole on the right-hand side. Now, the principal stress directions, so-called trajectories, in 2D, in two dimension, are here sigma 1, which is the maximum principal compressive stress, and sigma 3, which is the minimum principal compressive stress, or the maximum tensor stress, depending on the stress field. Here we have a circular hole under tension, and the tensor loading in this direction. Then the maximum compressive stress would have these trajectories, these directions here. So the joints, if a joint formed here, would follow these kind of curved paths here close to the circular cavity here, circular hole. The stress field around the elliptical cavity is slightly, or the elliptical hole is slightly different, but still there's a curvature in the joints, just like what you saw earlier. So what we have then is that the joints, they follow the sigma 1, and also in fact sigma 2 is in the joint plane trajectories, and they're perpendicular to the maximum tension sigma 3. So when a joint pattern forms, as you saw, they basically trace out the local stress field at the time of their formation. So I've illustrated this here. So in a way, when we look at a beautiful joint pattern or fracture pattern as we see here, we are looking at the local stress field frozen in time. Frozen in time, meaning that when the joints formed, like the curvature here, this is where we saw the lady standing earlier, the joints were following the stress trajectories, and after they formed, the stress field may have changed and so on, but the field that was operating when they formed, that is mapped out by the geometry of the joints. You see, for example, here's a joint you can trace. It's curved all the way to the fault, from this fault to the next fault. I've traced here one yellow joint, a little bit crudely, from this fault to that one, and another joint that is relatively straight going in this direction from the fault. So here's the fault, here are two other faults, and in between are primarily joints. Now, some joints, when they go from one limestone layer to another one, they maintain their orientation, or what we call strike in geology. Now, in between the limestone layers is a different rock, namely mudstone. And the mudstone is a very changeable rock in mechanical properties. It can be from basically mud, very soft, and then the stress from this layer would not be able to be transferred to the layer above, because the soft mud in between would not allow it. But if the mudstone has become really hard rock, with similar properties to the limestone layers above and below, then the stresses can easily be transferred from one layer of limestone to the other one, and then the stress fields may be very similar, as is the case here, and have a similar, the joints have a similar strike in this layer as in that one. So that's probably in this case the thin mudstone here was already relatively stiff and allowed transfer of stress from this limestone layer to that one. But that's not always the case. Definitely not. We come to that in a moment, but first I show you that in the case that the fractures propagate through many layers without much change in their orientation, that is, in their attitude, strike and the dip, strike and inclination, as you see here, then the mudstone had little effect on the local stress fields. So probably the mudstone was here relatively stiff, very, very thin layers of mudstone here. These are mainly limestone layers. And you see this set of faults, is in a way close to forming a beautiful conjugate set, as we see here in this rock physics experiment. So these ideal conjugate faults as should be forming when sigma 1, the maximum principal compression stress, is vertically orientated here. So they are close to, not quite, because you see some irregularities. There are other fractures here and irregularities here, but they're not far from being beautiful conjugate faults in a vertical section. This cliff is several tens of meters, around 40 meters, something like that. And this is close to Nash Point. This is close to Nash Point. So here we see the fracture going through the layers without much change in attitude. But as I said also earlier, it's not always the case. And we see here, not far from the other place, this is exactly the Nash Point. We see here an abrupt change in the orientation and the attitude of the joint from one limestone layer to another one. Let's look closely here. Limestone layer A, limestone layer B, and in between, A and C, and in between is B, which is a mudstone. Now, if you look at the orientation, you see that the orientation of the joint here in layer A, and the same here, is in this direction, whereas the joint orientation in layer C is completely different. Completely different. With these orientations meeting here, you see there's a big angle in between them. So that means when these joint sets were forming, layer A had a totally different local stress field from layer C. Why? Because in between was layer B, which is mudstone, and at that time, layer B, the mudstone, was probably mud, was very soft, very compliant. So the stress field in layer C could not really communicate with the stress field in layer A. And therefore, they had developed very different local stresses. In addition, they are close to a fault here to the right, not seen on this photo, that may have affected the local stress field here, but definitely the local stress field at the time of these joint formation in layer A and C was totally different. So one reason why many fractures in general and joints in particular become or stay short, propagate for a short distance, is that they become arrested, commonly at contacts in vertical sections like you see here, at contacts between mechanically dissimilar layers. So here are mostly limestone layers, but in between there are mudstones. And in addition, the mudstones, even if they're very thin, they can affect the stresses so that the fracture may not be able to penetrate through the mudstone here when it was very soft and becomes arrested. And you see here, this is the whole or large part of the layering. And then I have a close-up here. So the arrow here points to the place where I show the close-up here on this photo. And you see the joint here on coming close to the mud stone here, which was probably very, very soft. It's very thin and was very soft at the time. It cannot penetrate it, and it changes into three segments, two of which curve into the contact, and the third one simply ends abruptly. In any case, the joint becomes confined to this layer here and doesn't go through this layer there. So it becomes arrested. It is what we would call, if it's confined to one layer, we'd call it stratabound. Stratabound. Here are other examples, except in this case, because here we are dealing with the south coast where the soft rocks are really shales. So they are laminated and there are contacts inside them, inside the shale layers themselves. So here's limestone. All this here is shale. And these two joints, they end inside the shale layer. Why? Because they meet contacts inside the shale. The mechanical properties of shale can change very much inside a thick shale layer like here. Often, the shale is much stiffer with a higher Young's modulus, close to the limestone, and much softer, more compliant, lower Young's modulus in the middle part of the shale. So these two joints here, they are both ending vertically here at this contact inside the shale, and we see that they curve and become perpendicular to the contact, meaning that when they formed, the contact was probably what we call a free surface. That is a surface that doesn't tolerate any shear stress, so therefore it was very likely filled with fluid, very likely filled with fluid. Here we have another example of arrested fractures. Again, extension fractures like the joints, but these are mineral veins. In particular, these are calcite veins. This is again on the south coast of the Bristol Channel. And we see here a calcite vein. So this is the pile seen from a distance. And this is 1 meter here, my measuring tape. And here we see it close up. This one here and many other calcite veins, they tried to go through the shale. This is the laminated shale, but failed. So they become stratabound or layer bound. They're confined to a single layer here. I've showed you now many arrested extension fractures, namely joints and mineral veins, but of course faults, small faults, are often arrested as well. And here again on the south coast of the Bristol Channel, we see beautiful example of arrested small faults. You see my geological notebook here, which is around 15 centimeters in height here as a scale. And you see this beautifully clear fault, small fault here, goes through this limestone layer, goes into the shale, and then becomes arrested at a contact again inside the shale. So it becomes arrested here, deflected into this contact. In fact, fault B, again you see here, which is, as you see, is a reverse fault, or you could call it, in fact, a mini thrust fault, whereas this one is normal. This one also becomes arrested at a contact, but outside the photo here. So arresting of fractures is very common and keeps most of the fractures short. They propagate for a while and then become arrested. So they never have a chance to become large. So it follows from this discussion that we often have layers with fractures like we see here. So I just indicate the fractures just here, but of course they're everywhere along this layer. These fractures then become confined to a single layer and are called strata bound or layer bound. In this particular case, we are looking at very interesting fractures. This is close to the village of Kilve on the south coast of the Bristol Channel. These are so-called veggie fractures where a fluid, primarily groundwater, has gone through and made the fracture gradually more open. They were not initially of this opening here. This is later formed by water flowing through and making them wider or greater opening. So we have looked at many fractures now in cross sections, vertical sections, but now let's look at what they look like at the surface in plan view. So here again, my measuring tape is 1 meter, and you see, of course, students here for scale as well. And in this case, we see an interesting situation. We have these relatively large joints, kind of master joints or systematic joints, and then in between them, a lot of smaller joints. They fill in between the big joints. So again here we have a few relatively large fractures and a lot of very small fractures down to tiny little fractures like here and here. So we are seeing the pattern very clearly. Wherever we have a large sample of fractures, tectonic fractures, we will probably find that the small ones are very common and the large ones, relatively large ones, are very rare. So that's the situation we often deal with. We have here on this sketch here, we have a lot of small fractures. In plan view, we see that there are systematic joints, as I just showed you, the main joints, and then filled inside them or between them are so-called cross joints. There are various names, but here they are referred to as cross joints. So there are a lot of the smaller joints, then some larger joints, and then a very few either fracture zones, small-scale fracture zones like shown here, or if they're really cutting through many layers, more commonly faults, like you see here. So here's a normal fault. We have also small faults, as we saw earlier, that are strata bound. So these fractures here are strata bound, they're strata bound joints. These are strata bound faults. And then we have non-strata bound faults going through and maybe some systems of fracture zones as they're referred to here. So they go through. So the general observation here is that a lot of small fractures, many of which in layered rocks are strata bound or layer bound, and then a few larger fractures that go through many layers and are commonly faults. So to show you again from the field such an example, here is a normal fault on the south coast of the Bristol Channel, very close to the village of Kilve. And you see that the normal fault is very gently dipping here, is cutting through a lot of shale and limestones. And here you see, in contrast to what you saw the north coast close to Nash Point, the shales are very thick. They're very thick. Whereas there, the similar rocks, the mudstone was very thin, very thin. So here we see a normal fault, gently dipping normal fault, cutting through numerous layers. So this one is obviously not a strata bound one. It's non-strata bound, non-layer bound. And we can then go into the details of what we would expect to see in a normal fault like we just saw. If we go into the details, the fault we saw was in fact relatively small, but it still had a core, very thin one, and a damage zone. So these are the main mechanical units of any fault. And if one goes into details and starts to measure the fractures inside the damage zone, most of them tend to be very small. Most of them tend to be very small. So that applies, of course, to dip-slip faults, like this Nova fault here, and obviously to the strike-slip faults, many of which we have seen earlier today, particularly on the north coast of the Bristol Channel, where we started this lecture, this talk. And again, in the damage zone, not to speak of tiny little fractures that may be in the fault core, which is mainly of breccia or particulate materials, gouts and often clay and so on. In the damage zones, the fractures tend to be much, much smaller, of course, than the main fault itself. So again, here you would see same kind of distribution, a lot of small ones, and then very few large ones in any kind of fault zone or any kind of fracture system. And therefore, we normally end up with this distribution I show you here on the next slide. Now, this one is not from the Bristol Channel or from sedimentary rocks. This is from Iceland again, I've showed you before. And what we are looking at here is simply a plot of the size distribution of tectonic fractures in the rift zone of Iceland. And we have here 565 tectonic fractures that range from 0.1 meter to 7.7 kilometers. Here is an ordinary plot, in this case a power law, but we can fit these data also, at least in many cases, with negative exponential laws as well. But if you look here just at the power law, we can plot it first on a log-log plot to see if it's a straight line. And we see it would fit better with 2 or even 3, but often 2 straight lines. And there is, as I discussed earlier in these lectures, there is often a change where the break is here in the mechanics. So often the shorter ones would be of different types of fractures. Often in Iceland would be tension fractures, and the longer ones would tend to be faults. In the rift zone, of course, normal faults. But the main point here is to show you that we have this distribution, that we have a lot of small fractures. And then gradually, as the fracture size increases, the frequency goes down, and then there's only a very few large fractures. Now, these are plots where we have so-called cumulative distribution, meaning that in the first bin or first point here, there are all the fractures. In the next one, all fractures larger than 100 meters, large or equal to 100 meters. The next one, large or equal to 200 meters, and so on and so forth. That's how you get this kind of distribution. But the main point is this one here, that the distribution of the tectonic fractures shows that short ones are many times more common than large ones, which means in an earthquake that the rupture areas or rupture surfaces and slips would also remain small on most of the fractures. Why? Well, because the maximum slip on a fault during an earthquake has a linear relationship with the controlling length or the controlling dimension. So here is the controlling dimension, L, controlling length or controlling dimension. This delta U3 max sounds a little bit complex. This simply means that we are modeling the fault here as a so-called mode 3 crack. Some of them are modeled as mode 2 cracks, and joints would be modeled as mode 1 cracks. But for this fault here, we take an example of mode 3 crack with a maximum displacement. And tau is the shear stress that drives the fault displacement, is the driving shear stress. And then these are the elastic constant, Poisson's ratio, and Young's modulus. But the main point here is delta U, the displacement, the slip the slip in an individual earthquake has a linear relationship with the dimension of the fracture. There's a linear relationship between the slip in the earthquake and the dimension of the fracture that is causing the earthquake. So therefore, it follows that if the sizes of the fractures, if the lengths or the dimensions of the fractures, controlling dimensions, have a power law size distribution, then the slips will have a power law distributions, and the areas, the slip areas, will also have a power law size distribution, and therefore the magnitudes will have of the earthquakes will have a power law size distribution, as indeed they do. So the main conclusion, you could say, or main conclusions of these two talks I've given now on the tectonic fractures and the relations to earthquakes can be summarized as follows: that earthquake size distributions are a consequence of the size distribution of the tectonic fractures that generate the earthquakes. There's a linear relationship, as I discussed. And the fracture size distributions, which has been the main focus in this talk, are a consequence of the anisotropy and heterogeneity of the host rocks. More specifically, these include the layering. So the rocks are composed of layers with different mechanical properties, and differences in the rock properties, mechanical properties of the rocks in general, as well as existing discontinuities, particularly existing faults and other fractures. All of these have effects on the local stress fields and tend to arrest most fractures and keep them short, keep them small. So the result is that most fault slips and slip surfaces remain small, and therefore they generate small magnitude earthquakes. So this is the formal explanation for the power law size distribution of earthquake magnitudes, which was the main point here to be explained. I show here also just the typical origin of an earthquake. We have the fault, we have the hypocenter and the epicenter. And I should tell you also that all this discussion here, if people are interested in more technical aspects of it, is discussed in this paper here that I published this year, Statistical Physics of Fissure Swarms and Dike Swarms, which was published in this journal, Geosciences, now in August. So with these words, I say simply thank you very much indeed. And from now on, I say bye-bye.